Okay, there's more. So inflation gave us the lumpiness. We now say that the dark matter are these particles left over from the Big Bang. And we now can put together a story, a detailed story of how structure formed in the universe. So it started out, we had these little lumps. And according to this theory, which is called inflation plus cold dark matter, the first things that form are galaxies. And they're these big fluffy halos with stars at the center. And then clusters form. And then the clusters come together. And I didn't really talk about superclusters, but there's one slightly larger thing in the universe, which is a collection of clusters called a supercluster. And this theory tells you that the first stars form when the universe at redshift 10 to 20, galaxies mostly 2 to 5, clusters between now and redshift 2. And so it's a very predictive theory. It says that we form the universe from the bottom up. It's so predictive that you can falsify it. And that's what has driven astronomers to try to falsify it. And so far, this theory looks very, very good. It describes how structure formed in the universe. And this sort of says this. So if you take these ideas, if you take the lumpiness, put it on a computer, you get a universe that looks like the one that I showed you. I apologize, I don't do this better. But, okay. Oh, island universes. Galaxies are island universes. Let me just come back to that thought. This is the Hubble Deep Field, or the extremely Hubble Deep Field. And it really, you kind of want to pat Immanuel Kant on the back and say, yeah, they're really island universes, because look at these galaxies, they're all separate. They're all off by themselves. But if this idea about dark matter is correct, here's what the universe really looks like. What the universe really looks like is a cosmic web of dark matter decorated by stars. And so I've got to walk you through this. So the red, the color, the brighter the color, the more dark matter. And so you see that the dark matter is just connected. Every bit is connected. There's no islands in it, except for the voids. But there's no islands in this. And where the dark matter is densest, that's where the atoms end up. And then the atoms light up. And so we're missing all that. We don't see the cosmic infrastructure, which is the dark matter. We just see the decoration. And my best analogy for this, again, involves Chicago. So Hyde Park is very beautiful in the winter. And you walk down 58th Street towards the Quad, and they have put Christmas lights on all the trees in the Quad. But when you're a couple of blocks away, all you can see are the lights. And the lights are just floating there. And they look like galaxies on the sky. I guess if you're a cosmologist, they do. And then you get close up and you see that the trees are the dark matter that's holding everything together. They're the cosmic web. Okay. Dark energy. And now we're... so everybody's good with dark matter. It's just a new form of matter. Okay. So Sandage wanted to know about how fast is the universe decelerating. And in 1998, we found out that it's actually accelerating, not decelerating. And this is where you're required to tighten your seatbelt so that we don't have any injuries here. And this is kind of a matter of pride for those of us in the physical sciences, because Science magazine is one dominated by all that life science stuff, curing diseases and fossils. But in 1998, the breakthrough in all disciplines of science was the fact that the universe is not slowing down, it's speeding up. And so we were pretty happy with that, although a little discouraged. That's what we have to do to get on the cover of Science magazine. Okay, so let me take you back to this diagram. This is the diagram about the size of the universe. And remember, these are all droopy lines. And so the idea is to measure how much the universe is slowing down. And if it's slowing down a lot, it'll fall back on itself. If it's not slowing down very much, it will expand forever. And there's Goldilocks. So how do you actually measure that? And so this is the most technical slide I have. And so if you're ever going to concentrate, if you're ever not going to be texting your friends, this is the slide, and it will be worth it. So this is the Hubble diagram where he plotted velocity versus distance, and he got a straight line. And so let me tell you how this works. So he got a straight line. And so if you were measuring galaxy velocities and distances today, this is exactly what you would get. You would get this diagram, just a straight line, because that's what we did the first time. The expansion of the universe is just a scaling up. So it's just geometry. But the telescope is a time machine. And so when we look out in space, we look back in time. And so when we look at very, very distant galaxies, we're seeing them the way they were a long time ago. And if the universe is slowing down, then a long time ago they were going faster than they were today. And therefore, if you could measure velocities and distances of very distant galaxies, you would see a slight bending upward. And the bending tells you how much the universe is slowing down. Did you all get that? Okay, so it's really simple. It's really, really simple. But it's really, really hard. And why is it really hard? Well, measuring the velocities, we did redshifts. That's easy. You don't even have to call a plumber. You can do that yourself. It's getting the distances to the galaxies. That's really hard. That's where Hubble really messed up. And in order to do that, you need something like a standard candle. You need an object like a 100-watt light bulb, whose intrinsic brightness so that when you see it, if you see it and it's faint, it's far away. And you see it and it's really faint, it's really far away. You with me there? So if you had a standard object, then how faint it is tells you how far it is. Okay, so that's the problem. Hubble tried to use galaxies as standard candles. And galaxies come in different sizes. It just doesn't work. But there's a type of supernova, and you have an expert here, Roger Chevalier, is an expert on these supernovae. They're called type 1As. And actually, this comes back to Mr. Zwicky. Mr. Zwicky is the first one to study, Dr. Zwicky is the first one to study these and classify them. And we believe that they're standard candles because they are the thermonuclear explosion of a star that's mass is 1.4 times the mass of the sun. So they're just a big bomb. And so, the other cool thing is they're very, very bright. So here's a galaxy at redshift 0.63. There's a supernova. It's bright as the whole galaxy. So you can see them. So they're an excellent standard candle. There's one small problem. They don't happen very often, once every couple hundred years. So if you have a favorite galaxy and you want to measure the distance to your favorite galaxy, don't use a supernova. Now there is a Polish experiment where I won't talk about it. Although I am told you can tell Polish jokes to Polish people as long as you tell them slowly. Because the universe expands the same in any direction, you don't need a special galaxy. You can use any galaxy. And so here's the trick. Oh, I'll skip that slide. Here's the trick. You use these big CCD cameras. You take a picture today. You take a picture 3 weeks from now. You've digitized the two images. You subtract them, and you see if any galaxy has changed its brightness. And so the technological breakthrough is these big cameras. Okay, so here's a picture that I believe Saul Perlmutter and his group took, and look at that little area there, and look at that little galaxy there, and here's a picture they took 3 weeks later, and I've blown up the same area, and that galaxy looks the same, but that one, something happened, and you subtract the two, and something went boom. And so you can discover these supernovae. And then you can get the data and put it on a plot like this. So each one of these points represents a supernova. And oops, look at that. They're below the straight line, not above it. So that must mean, if you follow the original argument, That means instead of the universe speeding up, instead of the universe slowing down, it's speeding up. Wow. How can that be? Here are the two teams. One was led by Brian Schmidt. There they are in Aspen, Colorado. And the other team was led by Saul Perlmutter. And the person not shown here is the guy who figured out the supernova method, Mark Phillips. And so two teams made this discovery. And it was a very exciting discovery. I have their data. There we go. So again, I don't want to scare anyone with this data. You don't really have to stare at it. But just stare at this little box here. Because I want to tell an interesting sort of story about science sociology. So these are supernovae. This curve is an accelerating universe. That curve is a slowing down universe. And that curve is a coasting universe. So probably you would say, yeah, that sort of looks like a better fit, but boy, we're going to overthrow the idea that the universe is slowing down based on this data. So the data wasn't very good. So why did it get on the cover of Science magazine? So that's just a wonderful story that I could spend hours on, but I just want to say one thing. So these two teams were not surprised to find the universe speeding up. They were very competitive teams. They were surprised that the other team got the same answer. Because, so if the French for it is, they didn't have high regard for the other team. So they were highly independent. And that really, it was a big surprise, but two different teams getting the same result. Now, it didn't rise to the standard of another University of Chicago graduate. Does everybody know about the Sagan standard? Extraordinary claims require extraordinary evidence. So this is an extraordinary claim that instead of slowing down, the universe is speeding up. It did not rise to that level. But so what do? You take more data, more methods, and hopefully the signal gets stronger. We know of some examples where that doesn't happen, cold fusion. Right? You take more data, the signal doesn't get stronger. So this was really important. Science is self-correcting. Everybody wanted to get in on it. The Sloan Digital Sky Survey, which I had mentioned earlier, looked at, I forget altogether, they got about 900 supernovae. Other teams did the same thing. Also, there's another important criterion, and I want the plumbers to wake up now. So Sir Arthur Eddington, the person who, a theorist and the person who led the expedition to look at the bending of light and test Einstein's theory, had a criterion: no experimental results should be accepted until confirmed by theory. So now you've heard of bimodal distributional laughs. The first people to laugh are the theorists. They really get it. And then the slower plumbers. But so science is not a book of facts. It's also understanding. And so if a result doesn't fit in, then at some point maybe you should think that it's not right.